Okay, now we want to take a look at mathematical modeling and something called curve fitting and regression. So what we're doing is taking real data, we're laying it out, plotting it out, and saying, what does that shape look like? Does that look like a line? Does it look like a parabola? Does it look like something else? The examples we're going to focus on, because we're just studying lines, are going to have a kind of linear shape. As we progress through the course, we will look at other types of shapes and use other equations to model data. Okay, so for this first one, we've got years and we have average monthly cost for health insurance. What I've created over here on the right is something called a scatter plot. And that's just to make sure what shape the data represents. Okay, so this one, when I plot it out, and you notice at the bottom here, my x's are the years since 2009. I'm not putting the actual year. That's a very standard math science kind of thing, is to make the first thing time zero, year zero, whatever. Then on the right, I'm sorry, on the y-axis column, we have the costs, and I just went in increments of 50. Plotting it out, each of those ordered pairs, 0, 293, 1, 333, etc., we do have a very linear shape. So that means kind of steady growth. And it is growth because it's going up from left to right. So now that I have an idea that it really could be modeled pretty accurately with a line, I'm going to come up with that equation. Okay, so we picked two data points. Now for our purposes here in the homework, they'll just tell you, use these two data points. I chose kind of in the middle type of points just because, I don't know, just it was random. First thing, anytime we find the equation of a line, of course, is to find the slope. So the difference of the y's over difference of the x's, and I got 15.7. Then I'm going to pick one of my points, I just went with the smaller numbers, and plug it into our point slope equation. So the y minus the y coordinate equals m times the x minus the x coordinate. Simplifying all that, we come up with this equation here, y equals 15.7x plus 317.3. So what this is telling me is that if x stands for the years since 2009, when I plug that in, my y should tell me what the average monthly costs were. So let's apply that. Here's our model. If we want to predict for 2017 and 2024, we first, you notice, in both cases, have to figure out what the x is. Remember, I can't just put in 2017. I have to say, how many years is that since 2009? So I take 2017, subtract my start year, and I'm going to use x equals 8. Similarly, for 2024, we calculate x to be 25. Plugging those into the formula, the model that we came up with a minute ago, we'll come up with $443 approximately in 2017 and a whopping $710 in 2024. Now that assumes that the conditions remain relatively the same as they have been at the beginning when we had our data. What we're doing here is going beyond the data. That's called extrapolation. And that can be a little bit dangerous. It's not nearly as accurate as the further out you go, just like your long range forecast, right, with the weather. So that's how we can do it using specific points. But is this really the best model? What if I had chosen two other data points? My equation would have been slightly different. Would that have been a more accurate model? Well, there's something called the line of best fit, and we're going to look at how to do the same problem with that in the next video.